Okay, everybody, it's time for our second talk of the day. Our speaker is Min-Chun Wu, and he'll be speaking about a topological approach to inferring the intrinsic dimension of convex sensing data.
Okay, thank you. Yeah, thanks for everyone coming to my talk. And yeah, today I'm talking about this title. So I will define what we mean by convex sensing and what is its intrinsic dimension and how we use topology to infer the intrinsic dimension. Okay, so let me start with some motivation from neuroscience. So there is a special kind of neuron in neuroscience that they call it place cells. And this kind of place cell have a special property that they kind of sense the locations in the following sense. So as you can see, there are three heat maps here. And actually the rectangle represent the same environment. Yeah, when you put an animal in the environment, they record the activity of three different place cells in here. And they discovered that one may treat the 2D environment. So you can see a rectangle 2D environment here as a stimulus space containing the location stimuli. So for place cell, actually one can treat each location in the environment as a stimulus, stimulating the behavior of the neuron. And actually the color here records the firing rate of the different place cells. So firing rate is the probability of firing. So for example, if I put a mouse in the environment and record the activity of place cell 1, then the blue basically indicates that there's a very low probability that this cell will fire at this location. And the red color here basically means there's a high probability that the cell 1 will fire when the mouse is in this location. So as you can imagine, different place cell will have different kind of locations that represents whether there's a high probability or low probability, whether you will fire or not. And you can observe that actually for this kind of firing rate function for different place cells, the super level sets of these functions are approximately convex, right? Because when you cut this ratio and just collect the points, the locations that is above that ratio, then you can see they are approximately convex.
Min-Chun, can I interrupt you quickly with a question from the chat?
Oh, sure.
When you say the location, are you referring to the location within the brain or within the physical environment?
The physical environment, actually. So it's the 2D environment. It's not the brain. So as I should say, place cell, the discovery of place cell is kind of, some people say is a miracle because it has such a simple interpretation of how the neurons fire with the outside world rather than the network connecting with each other. So place cell is quite special in that sense. So in general, we have no idea how the stimulus should be looking like. So for place cells, the stimulus space is kind of obviously the 2D environment. You can see the locations. And for general neurons, we don't have that kind of access to the stimulus space. What we have is this kind of spectrum data. We can record for different neurons when they kind of fire. So these vertical lines records the timing of the different neurons firing. And we only have access to this kind of thing. And actually, if you use some kind of sliding window trick, then we can actually estimate the firing rates for the same stimulus, but we just have no access to the stimulus space. So natural question now is, if solely from the firing rate data, if we just have access to the firing rate data to the to several different stimuli, can one recover the stimulus space? In particular, can one recover the dimension of the stimulus space? So the main focus of this talk, I'm going to tell you how we kind of figure out this dimension using some mathematical framework that we construct from the observations of the place cell behavior. We call it convex sensing. So in order to build this framework, we use a kind of function called quasi-convex. So we say that the function defined from Rd to R is quasi-convex if all of its sublevel sets are convex. This is kind of mimicking the firing rate function property of the place cell. So as I recall that for place cell, the firing rate function have the super level set being convex. So we use a function that having this kind of property to represent our firing rate function of neurons. And the basic setting for our convex sensing problem is we assume we have direct access to a data matrix looking like a function value applied on different points where there are some unknown quasi-convex functions which represent the neurons or the firing rate of the neurons. And we assume there is an unknown stimulus space, which is open convex in the RD, we denote it by K, which is the common domain for the functions. So you can think of that as a special case for not special, a generalization of the place cell discovery. And we assume that there are some unknown point cloud, which is in K, which are the sample or the stimuli that is encountered in the stimulus space by the neurons. And the convex sensing problem is, suppose we only have access to this matrix, which are the function values evaluated on these points. Can we recover the information about the stimulus space, the functions, and maybe the stimuli or the point cloud from just looking at the matrix? And in particular, I'm going to focus on how do we recover the dimension D where the K is embedded in RD, which is open convex. So yeah, I'm going to explain how we solve this problem in this talk. And in order to make the problem regular, so we make some regularity assumptions on the framework that I just described. And the first thing is how the points are encountered, how the samples are generated. So we assume there is unknown probability measure pk that is supported on K. And the probability, the point cloud is actually IID from the pk. So how we describe how the samples are taken is it is IID from some unknown probability measure defined on the stimulus space. And in order to make the problem regular, we also assume that the pk is equivalent to the Lebesgue measure restricted on K. That is, they have the same measure zero sets. Measure zero for one measure is the same as measure zero set for the other. And we also assume the functions have the level set of the function has pk measure zero. So when the function, because the functions are quasi-convex, the sub-level sets are convex. When you increase the threshold, actually you have an increasing sequence of convex sets. This kind of assumption guarantees that this kind of increasing process is kind of continuous without any kind of major jump. So we assume the level set has pk measure zero. So for convenience, we denote the collection of function and the probability measure as a regular pair if the above conditions are satisfied. Yeah, just a convenience notation. And notice that the dimension actually depends on the regular pair. Yeah, because the dimension is basically the dimension of the common domain of the functions. So we denote, to be more clear, we denote the dimension by dfpk. Yeah, just kind of emphasizing its dependence on the regular pair. Okay, so far I have set up all the problem set up mathematically. So now let's look at some topological tools topological tool that we develop for the dimension inference purpose. So the main thing we use is motivated from the Docker complex of relations. And let me kind of define our version here. Suppose we start with a regular pair, and then we define the following Docker complex. We call it geometric Docker complex. And this geometric Docker complex is a multi-filtration simplicial complex. It is indexed over 0, 1 to the n. And the simplicial complex at the index T1 to Tn tuple is defined as the nerve of the following collection of sets. And these sets are, so you can notice that there are m sets in this collection, and there are m functions. So the index I here refers to the ith function. So the KITI is actually, KIT here is the sublevel set of Fi with the pk measure T. Let me explain with a figure, with a picture, yeah. So the picture is, they have the common domain K here, and we know that the functions are quasi-convex. So if you increase the threshold, then actually the convex set will grow from the empty set to the whole K. And because pk is a probability measure on K, so the total measure is equal to 1. So there is a unique moment where the sublevel set has exactly the measure equal to T. We denote this set by KIT. And for different functions, we index over the T1 to Tn, we just collect the KITI, which are a sublevel set of Fi having the measure Ti. And then using this collection, we construct the nerve. We denote it by the Docker. We call it the geometric Docker complex at this index. So this is a multi-filtration over 0, 1 to the n. But one thing to notice is that this is not computable from the data matrix because you see there's no matrix in here. We just use the underlying mechanism to construct a geometric Docker. Okay, so this is the first type Docker we consider. And the second type Docker is defined from the matrix. So if we start from the matrix, we can actually define a, we call it empirical Docker complex as follows. It's again a multi-filtration over the index 0, 1 to the n. And the definition is a generalization of the original Docker complex of relations. And I'm not going into too much details here, but you just need to know that this Docker is actually directly computable from the matrix. And yeah, for people familiar with Docker complex, you can see this is a thresholding procedure that is used in the same way that the Docker of relations is used. So yeah, this is a generalization, classical Docker relations. Yeah, we can, if people are interested, we can talk about this more in the Q&A session. And yeah, for now, you just need to know it is computable from the matrix. And why we care about these two Docker is because they have the following convergence property. But this time, the empirical Docker and the geometric Docker are multi-filtration. So we have to decide the metric to compare these two multi-filtrations. And the metric that I use is defined as follows. So suppose we have two multi-filtrations, K and L, and their index over Rm. Then their simplicial interleaving distance is defined as follows. So we take the infimum among all the epsilon, where you shift the index of the other, it can cover the other one. So it is an infimum epsilon greater than 0, where K is contained in L plus epsilon and L is contained in K plus epsilon. And this kind of L plus epsilon or K plus epsilon is actually the shifting of the multi-filtration index. So when you have a multi-filtration, when you plus epsilon is a new multi-filtration, where it is the value of the index at T1 to Tn is original multi-filtration at index T1 plus epsilon up to Tn plus epsilon. So roughly speaking, we just shift the index of the multi-filtration and compare whether one can cover the other. And we figure out the smallest epsilon possible that can fulfill this and denoted by the simplicial interleaving distance. And if this is not, no such epsilon exists, then we just define the distance as infinity. And using this interleaving distance, actually, we prove the following theorem. We call it interleaving convergence theorem. Suppose the M is a matrix sample from the regular pair. Then as the number of sample goes to infinity, the empirical Docker complex will converge to the geometric Docker complex in interleaving distance improbability. So roughly speaking, we can use the empirical Docker complex to approximate the geometric Docker complex if we have sufficient many samples. And okay, so now let me introduce how we use these two Dockers to do the dimension inference. And here I will introduce the geometry idea first carefully. So suppose we fix the regular pair and fix a point in the stimulus space in the domain. Then we know that the picture is looking like this. We have this region K and the point is in here. Then for each of the function Fi, we can find the Ti such that the Ki Ti actually touches X on the boundary. These are so recall that these are the sublevel set of the function Fi having the major Ti. And because the sublevel set are basically continuously growing in the domain K, so there is a moment where this kind of sublevel set touches X on boundary for each of the functions. And then if we reduce the Ti a little bit continuously, then actually this kind of d minus 1 cycle will show up if your X is kind of central enough. And if we reduce the TIs more, then this kind of cycle will kind of disappears. And notice that this process construct a filtration, one-dimensional filtration of simplicial complex. If you use the nerve of this collection of sublevel sets. And if we compute the k-dimensional persistent homology of this filtration, then we can figure out which interval is the longest in dimension k. And then we can change the points in the region and consider different filtration and figure out which point will give you the longest possible persistent interval, k-dimensional persistent interval. And then we denote the longest possible persistent interval by this notation, LK-FPK. Okay, so this is a definition. This is a construction that we can do with this regular pair. With this regular pair, we can, for each of the non-negative integer, we can define LK-FPK, which denote the longest possible persistent interval construct in this way. And because we use the nerve of the collection of these sublevel sets, it is nothing but the geometric Docker we just talked about. So formally, we can use the geometric Docker to define this value. And here is the details. So I'm not going to go through these details here because of time constraint. So yeah, what you need to know is for each of k, we can formally define using the geometric Docker that we just defined. And not surprisingly, because there's also empirical Docker. So we can also come in from, starting from the matrix N, we can use the empirical Docker to define a similar value LKM. And here are the details. So yeah, you just need to know that this value can be defined when you can be computed from the matrix. So starting from the matrix, we can just go through the following computations and eventually get this value. And the definition is similar to the one that is used for the geometric Docker. And not surprisingly, because the empirical Docker converges to the geometric Docker, so not surprisingly, the value defined from the matrix will converge to the value defined from the regular pair. So if our matrix is sampled from the regular pair, as the number of sample goes to infinity, then for each of the k, LK, and then will converges to LK, FPK in probability. And the rate of convergence is independent of k. And the reason is very simple is because the convergence level is in the simplicial filtration or simplicial complex level. So when you take a homology, take persistent homology and take some other constructions, it will not influence the convergence rate. And people might ask why, so how about this connects with the dimension? And here is the connection. We call it the lower bound lemma. So this lemma is stating that for k is greater than or equal to the dimension, then this LK-PK that we just defined must be equal to 0. Yeah, the intuition is very simple. It's because in d-dimensional space, it is impossible to form a d cycle or above dimension cycles. The best you can form is a d-1 cycle. So the lower bound lemma holds. So a corollary of the lower bound lemma is we can define the following lower bound dimension. So if we define it as the maximum of the k such that LK-PK is not equal to 0, and then we plus 1, this must be a lower bound for a dimension. So using the value that we just defined, which we can approximate using this value, we can actually get an idea of what is a lower bound for the dimension. Yeah, but so far it's just a lower bound. People might ask, so what if we want the true dimension, not just a lower bound? So to answer this question, we provide a sufficient condition for the lower bound equal to the true dimension. And the condition here, we call it complete. So we said the regular pair is complete if the following set is non-empty. And this cone here is the Conning Hall, and this is just a gradient. So if we can find a point in the domain such that the Conning Hall of the gradient of the functions will be the whole space, then we call this regular pair complete. Yeah, this is kind of quantifying what we mean by a point to be central enough. Yeah, a point that is in here, we consider it to be central. And using that point and construct the filtration, actually will give you the d-1 cycle that we desire. So not surprisingly, if our regular pair is complete, then the lower bound that we just derived from the regular pair will be equal to the true dimension. And the next question, people might say, okay, but we just have the matrix. Can you tell me whether the regular pair is complete just by looking at the matrix? And the answer is, yeah. So how do we know whether the regular pair is complete? So we provide the following way that we can use to test whether the regular pair is complete by just looking at the matrix. So first we define this set. This is a subset of the column index. So collect the A such that this property is satisfied. Yeah, don't worry about the details. This is basically, you only have to know that this set is definable from the matrix and computable from the matrix. And the next theorem can be helpful for testing whether the regular pair is complete. So suppose our matrix is sampled from the regular pair, then as the number of sample goes to infinity, this value will converge in probability. That is, you count how many points in here and divide it by the number of columns, then this value will converge in probability. And how we use that to test the completeness is if this limit is positive, then this regular pair must be complete. So this is a way that we can compute this property and decide whether this is a positive number, decide whether the limit is a positive number or it's a zero. Then we can decide whether the regular pair is complete. Okay, so these are all the theory parts and the construction part. Let's look at some simulation experiment that I carry out. So first, we want to test whether the method works in some way, in the way that I just talked about. So first, we fix a dimension D, that is in 3, 0, 4, or 5, and then we randomly generate 10 quadratic functions, representing the quasi-convex functions. And then we uniformly sample 350 points from the unit ball in RD, represent the sample. And then we can construct this data matrix. So now, after step 3, we just forget about 1 and 2. We just assume we have this matrix and we are trying to figure out the dimension D here. And how I do that is I implement, because we have to know how large is the variance because the LKM is a random quantity. So we have to figure out kind of how large is the variance to decide whether it's a positive number or not. So what I do here is I implement the subsampling procedure on the columns, which are the samples. So I fix an NS that is 50, 150, or 200, and uniformly sample NS columns from the matrix, and denote the result by NNS. And instead of compute the LKM, we compute LK and NS here, so that we have some variance in there, and we can repeat this subsampling procedure many times. So here we choose 100 times. Eventually, we'll get 100 different values for this because we get different 100 submatrices. And then to represent these 100 numbers as a summary, we use the box plots and see whether it is kind of 0 or it's not 0. And here are the results. So for dimension equal to 3, we are kind of expecting L1 and L2 to be non-zero. And as you can see here, for 50 points of sampling, we really get this kind of box plots. And for L3 and above, they just have noise or nothing. And for 150 points, we see the variance actually shrinks. Supporting the law of large number that I just illustrates. And for 200 points, the variance becomes shorter, and still only L1 and L2 shows up to be non-zero, and these are just noise. So we can decide the dimension is equal to 3 here. And the same behavior for dimension 4, L1, L2, L3, and the variance just shrinks. And for dimension 5, the same procedure still holds, and we can still decide the dimension is equal to 5. So this kind of demonstrate the usability of this method. And that's it for my talk. Thanks for the listening.
Please unmute yourself and applaud the speaker.
Thank you.
So thank you for the excellent talk. Are there any questions from the audience?
Hi, thank you for your talk.
Hi.
Just a quick overview question. Why do you call it convex sensing instead of non-convex?
The reason why we call it convex sensing is because we kind of treat the problem as sensing the space using. You say why don't we call it quasi-convex sensing, right? The reason is because we use this kind of function, and the main thing we use is the sublevel set, which are convex sets. We're kind of treating the problem as using the sublevel set to sense the space. And that's the reason why we call it convex sensing.
Thank you.
Okay.
So I have a quick question myself.
Sure.
Have you applied this yet to any of the non-simulated data? Are
Yeah,
there any challenges in doing that? Okay, thank you.
Yeah, actually, I have been trying to apply this method to especially neuroscience data. Yeah, because the motivation is from neuroscience. Yeah, but the data I have in hand is the sample size is kind of too small, so that the convergence is not that quite clear. So I think that's the main challenge. Yeah, I haven't tried the method on larger data, so I don't know whether there will be some difficulty there. But I think as long as the number of samples is sufficient, the convergence property should show up, and we can figure out what dimension we should choose.
So when you say the data is very small, you mean like the neuroscientists are only collecting information from like 20 place cells as opposed to 500? Is that the idea?
Yeah, actually, it's not the problem is not the number of neurons; it's a number of stimuli. So, for example, yeah, because the convergence is actually when you have more and more stimulus, when you have a more and more stimuli, then the convergence property will show up. And yeah, for many reasons, maybe yeah. So the data I have in hand is like they only have 50 stimuli, or at the most less than 100. So that kind of size does not guarantee that convergence property really shows up very clearly. So yeah, that's the main challenge for me.
And even when you have that little data, so maybe it's very hard to establish the cutoff, can you definitely say, give some like fairly confident bound on the dimension, like it's not 20 dimensional or something maybe ambitious, something that like, you know, something like that, or even that it's still hard to say?
I don't really get your question. Sorry. Can you repeat that?
So if you can go back to the plots at the end.
Okay. Plots to the end here. Oh, not this one.
Yeah.
Right.
So if I understand correctly, right, the variance of these box plots shrinks as you get more stimuli. But say for example, in none of these experiments did you observe anything 6-dimensional?
I haven't tried 6-dimensional, honestly. Yeah.
Oh, I see. So it may just be a question of what you've tested for. Okay.
Yeah. I tested for up to dimension 5. Yeah, dimension 6 actually 200 points. I mean, 350 points may not be that sufficient, and the convergence is not that clear. So that could be the problem. And also another thing is, you can see this is actually decreasing. So the signature of different dimensions is actually decreasing. And it looks like maybe the decreasing rate could be exponential. So that could be a main problem if we go to dimensions that is too high. So yeah, if there is a method that we can actually just kill the other things and keeping this, for example, like dimension 5, if we can only try to figure out another estimator. So far the estimator we use is LK here, the longest possible per k-dimensional persistent interval. Yeah, actually there is a benefit using this. If there are really too small sample size and you cannot really sure whether the dimension is maybe like 5, then you can still get a lower bound. Yeah, I mean lower bound is guaranteed, but the true dimension is not that always guaranteed. You will have sufficient many data points to guarantee that. So yeah, does that answer your question?
Yeah, and I'll add one more question, then I'll let other people ask.
Okay, sure.
I don't know how they think, but do the neuroscientists who think about things mathematically have an intuition for what the dimension of the space should be, or is it something that is translatable into something that makes sense in the neuroscience literature to your knowledge? And if you told them it was 5 or 3 or 10, is there something that they could do with that, or would it be surprising?
Yeah, actually it would be surprising because especially, for example, like if you think about the neurons that is in charge of the smelling, then there are so many ways that can, because the stimuli are basically chemical compounds, and the chemical compound, there are so many ways you can kind of quantify the properties, and they are kind of discretely connected atoms together, and it's quite difficult to figure out a continuous space that you can embed all the chemical compound into there. So they kind of design a lot of like manually labor features for them. The dimensions are super high, but when they do the embedding, the connections is not that continuous. For example, like when the neural activities are kind of similar for two chemical compounds, but their features will kind of plot these two different compounds in the very far away places using their features. So there's a very unnatural thing, or maybe there are some problems in the feature, or they kind of mix the features together so that this kind of weird behavior will happen. So in the neural world, I mean, the world that neuron kind of recognize these compounds are similar, but the human design features are kind of very different. So there's a main thing. So their dimensions are always very high. So if you tell them, okay, the intrinsic dimension should be very low if you use this kind of thing to think about it, I think that will not be too surprising because so far the features are too manually designed. It's not very natural features.
Thank you. That's really, really interesting.
Okay.
Any other questions for our speaker?
I'll ask one more question. How computationally expensive is it to do these plots?
Yeah, that's a very good question. So normally in practice, if you want to do some computation, maybe you want to set an upper bound for the persistent homology computation, because the most expensive part is for the persistent interval computation. And actually the details is in our paper on arXiv. As far as I remember, the computation complexity is big O, the number of functions to the upper bound you set for the computation of the lower, the persistent interval times the number of samples. Because we basically go through all the samples. So there is a linear scale for the number of samples, the number of columns. And for a persistent interval computation is because there's a cubical power to the number of phases, as far as I remember. So it's n to the 3d up times n. Yeah, so that's the computational complexity. So d up is the upper bound you set for the persistent interval computation. So yeah, that's the answer. Yeah, actually, we're trying to kind of reduce the computation cost by maybe focusing on just several points. So as I define here in the completeness here, yeah. So this set actually kind of collects the columns that we think is central. And if we focus computation only on this, then we can reduce the computation a lot, depending on the data you have in hand. So that's one way that we can reduce it. Yeah, but for a persistent interval computation, yeah, so far I think the best worst case complexity is to the cubic number of phases. So that part cannot be reduced. Okay.